Imagine you run a website. At the end of the day, you want to know how many unique people visited, not how many requests, unique humans. The naive answer is to keep a set of every user ID you've seen and count it at the end. That works, until you have 1 billion users a day. Now your set is many gigabytes of memory just to answer one number. Redis has a command for this exact problem. It uses 12 kilobytes. Always, 1 billion users, 10 billion users doesn't matter. 12 kilobytes, and the answer comes back accurate to within 1%. The data structure behind it is called HyperLogLog. It has a strange name and an even stranger trick. By the end of this video, you'll know exactly how it pulls that off. The straightforward way to count distinct items is to keep a set. As each item arrives, add it. Adding an item that's already there is a no-op. At the end, the size of the set is your answer. It's exact. The cost is paid in memory. A typical user ID, stored as a hash table entry, takes around 16 bytes when you count the pointer, the hash, and the slot overhead. 1 million distinct users is 16 megabytes. 100 million is 1.6 gigabytes. 1 billion is 16 gigabytes, and that's per metric. If you also want unique users per page, per region, per hour, you're now spending more on counting than on serving the actual product. We don't always need the exact answer. So let's give up exactness and see how cheap we can make this. Before we count anything, one fact about hash functions. A good hash function, anything cryptographic, or any modern non-cryptographic hash like Roman 20 hash or murmur hash, has a specific property. The output bits are uniformly distributed. If you feed it any stream of values, clustered, skewed, biased, doesn't matter. The output bit patterns look statistically indistinguishable from random. Each output bit is, on average, a fair coin flip. This is the hidden gift we're going to abuse. Once we put a value through a hash function, we can stop reasoning about the value. We can reason about a uniformly random binary string instead. And uniformly random binary strings have very predictable statistical properties. Properties we can exploit to count without remembering. Here's the trick. Look at one bit of a uniformly random number. It's 0 with probability 1/2. Look at the first two bits, both 0 with probability 1/4. The first k bit's all 0, probability 1/2 to the k. Now flip this around. If you've seen many random binary numbers, eventually one of them will start with a long run of zeros. The chance of seeing a run of length k somewhere in n draws is roughly n/2 to the k, so if the longest run you've ever seen has length k, the most likely number of items you've drawn is about 2 to the k. The maximum leading zero count, in other words, behaves like the logarithm of the cardinality. Take it back as a power of 2 and you have your estimate, almost free to compute, one small integer per stream. There's a catch. The maximum leading zero's estimator is right on average, but it has terrible variance. Imagine you've added 1,000 items. Most of the time, the longest run you'll see is around 10 zeros, giving an estimate near 1,000. Good. But every once in a while, by sheer luck, one of those 1,000 hashes happens to start with 20 zeros. Now your estimate jumps to 1 million. And we never deleted that observation, so the bad estimate sticks for the rest of the run. The estimator is unbiased, but a single run can be off by orders of magnitude. We can't ship that. The classic fix in statistics is to average many independent estimators together. Each one is noisy. The average of many is much less noisy, so we need many independent leading zero counters, not just one. Here's the move. We split each hash value in 2 parts. The first few bits, let's say 5 bits, pick which counter we're going to update. 5 bits give us 32 distinct bucket addresses. The remaining bits are what we count leading zeros on, just like before. Each item goes to exactly one bucket, chosen by its hash, and updates that bucket's running max. Because the hash is uniform, items are sprinkled evenly across all 32 buckets, and each bucket sees an independent random subset of the stream. So now we have 32 independent estimators of the cardinality of the items that landed in that bucket. Combine them carefully, and we'll see what carefully means in a minute, and our wild variance shrinks dramatically. The cost? One small array. That's it. Putting it together, here's the algorithm. To add an item, hash it to 64 bits. The top p bits become the bucket index. The remaining bits are scanned for leading zeros, and we record 1 plus that count, call it row. We update the bucket's stored value to the max of itself and row. That's the entire add path. 2 integer ops, 1 comparison. To get the count, we apply a specific formula. Take each bucket's stored max, raise 2 to the negative of it, sum across all buckets, and divide a constant times m squared by that sum. The constant alpha is a small bias correction. We'll see why this exact formula in the next scene. The point for now: cardinality estimation has been compressed into one tight loop and one closed-form expression. How accurate is this? The standard error of the HyperLogLog estimator is approximately 1.04 divided by the square root of m, the number of buckets. At 16 buckets, your error is 26%. Useless. At 4,096 buckets, your error drops to 1.6%. At 16,384, Redis's default, your error is 0.81%. And the memory? Each bucket holds at most a 6-bit number, because no leading zero count of a 64-bit hash exceeds 64. 16,384 buckets times 6 bits comes to 12 kilobytes. 0.5% error, 12 kilobytes, regardless of whether you've added 100 items or 100 billion. That's the trade. One knob, m bigger m, lower error, more memory. Let's see this in production. In Redis, you call PFADD with a key and an item, adds an item to a HyperLogLog. PFCOUNT gives you the estimate. Constant memory, constant time per operation. BigQuery, Snowflake, and Presto all expose this under the name PFCOUNT distinct. Across petabyte-scale tables, it returns in seconds where exact distinct counts would scan for hours. There's one more property worth knowing. HyperLogLog sketches merge. If you have one sketch on web server A and another on web server B, the merged sketch is just the element-wise max of their bucket arrays. So you can shard the work across many machines, then combine without retouching any of the original items. That's why every distributed analytics system you've heard of uses this. HyperLogLog isn't alone. It's part of a family of probabilistic data structures called sketches, and each member answers a different question while paying constant memory. Bloom filters answer membership. Have I seen this item before? CountMin sketches answer frequency. How often did this happen? tdigest and KLL answer quantiles. What's the median? What's the 99th percentile? Each one sacrifices exactness for a guarantee about the size of its error. In return, it gives you a data structure whose size doesn't grow with the data. The lesson is one of the most useful in systems engineering. If your problem doesn't truly need exactness, the right approximation can be thousands of times cheaper than the right answer. HyperLogLog is the one to remember when the question is, how many distinct things have I seen?